everyone. Today we start with the senior design and research presentations. And first online is Michael Bryan. So let me tell you a little bit about him. Michael Bryan is a candidate for the Bachelor of Science degree in both General Engineering and Physics. He has worked several REUs in the past couple of years. In the summer of 2010, he works at Harvard on a project where he was trying to design and fabricate and test something called paper-based micro-electromechanical systems, or MEMS. He continued with that work in summer of 2011, and the primary emphasis at the time was to optimize a paper-based MEMS 3-axis accelerometer. So there's a patent pending on this work, currently at Harvard. In the summer of 2012, he worked at the University of Maryland, College Park, on a project which was concerned with microrobotics.
Just programming, helping him, the coordinator in.
He's been a lab instructor for Eastern Nazarene College in the last 3 years or so. So today he'll be speaking about some of the work he's been doing on earthquake prediction, and the title of his talk is Analyzing Anomalies in the Ionosphere Above Haiti Surrounding the 2010 earthquake. So,
thank you. Thank you all for coming. My project focuses on the 2010 Haiti earthquake. So to begin, first we need to understand a little bit about the basics of earthquakes. I'm sure most of you are familiar with plate tectonics. Basically, the Earth's crust is made up of these tectonic plates that are moving around, and on the border of two plates, you can have various types of motion, but a problem arises when one of the plates gets stuck, and then when it releases, it kind of gets a more sudden movement, and that's what causes earthquakes. So, of course, we would like to be able to predict these earthquakes to give enough time to maybe evacuate cities or otherwise prepare ourselves for these events. So, currently there are several methods of earthquake prediction, none of which really give us enough time to prepare ourselves. But we have a recurrence frequency, seismic gap theory, the emission of low-frequency electromagnetic waves before earthquakes. You can also observe strange animal behavior before an earthquake. But there are also changes in the atmosphere, and that's what my project focuses on, and mainly the perturbations in the ionosphere. So, of course, we need to know what is the ionosphere. It's part of the upper atmosphere. It's composed of mainly electrons, but also other charged atoms and molecules that surrounds the Earth. And this ionosphere plays a very important role in radio propagation. So if you can imagine radio waves shooting off towards space, depending on the characteristics of these waves, they can either be reflected by the ionosphere back down to Earth, they can be absorbed, or they can pass through the ionosphere, maybe with some sort of deflection. But what my project is based on is this right here. Prior to seismic events, changes in electron density can be observed in the ionosphere. So the rock in the Earth's crust prior to an earthquake gets stressed a lot, and this stress causes an electric field to form. And this electric field starts a sort of chain reaction which results in changes in the electron density in the ionosphere. And this electron density is simply the concentration of electrons, usually measured in number of electrons per centimeter cubed. So in order to observe this effect, we looked at the earthquake in Haiti, which happened on January 12, 2010. And so to see this disturbance in electron density, we need to know two things. We need to know the actual data of this electron density, And then we need to compare that with what our atmospheric model predicts this electron density to be. And then whatever variations there are between the two, we know is caused by some outside disturbance. So in order to get the actual electron density, there was this Demeter satellite that was orbiting above Haiti around the time of the earthquake. And this satellite was carrying various scientific equipment. Primarily, what I'm interested in is this ISL probe, which measures electron density, which of course is really good. And then the model that we use is called the Parameterized Ionospheric Model, otherwise known as PIM, which is a physics-based global ionospheric model that takes into account the energy coming from the sun, otherwise known as the solar flux, the state of the Earth's magnetic field, the amount of solar activity, or the sunspot number, and the time of the year, because there are seasonal variations in the ionosphere. So it takes in these parameters and produces an electron density profile, which gives us an average background behavior of the electron density in the ionosphere. So this model, we can look at what it predicts for the electron densities leading up to the earthquake. So this graph right here is a graph of electron density versus latitude. And here this green line represents Haiti. And so this is an ensemble of measurements, or of predictions, that this model creates for this time frame, which is approximately 4 months before the earthquake. So I'd like to point out several key features of this graph. Over here on the left, we see these humps in the electron density, possibly one here. But between about 20 and 60 degrees latitude, it remains fairly flat. And then if we look at the month leading up to the earthquake, same kind of thing. You see these humps here, and then it gets flat over here. The month right after the earthquake, it's the same story. It gets interesting when we look at the actual data that we got from the Demeter satellite. Again, this is an ensemble of data taken over the course of this time frame here. As predicted, we get these humps over here on the left. However, over here on the right, about between 20 and 60 degrees, the model predicted it to be flat. However, we see this hump starting to form right here. And then if we look at the month right before the earthquake, this hump gets larger. And then right after the earthquake, it starts to go away. So this hump isn't predicted by the model. So we know it must be caused by some outside disturbance. We would like to say that it's the earthquake. However, there are other possibilities that could cause this hump. So we looked at other typical parameters that could cause this disturbance. We looked at the DST, or the storm time index. We looked at the KP, which is an index of geomagnetic activity. And we also looked at the solar flux and the sunspot number. I'd like to point out that for the DST, values greater than -50 are considered negligible. For the KP, values less than 4 are considered quiet. And for the solar flux and the sunspot number, values less than 90 are considered quiet. So we can get data from NASA and National Geographic for these parameters and look at the time frames that we looked at before. And indeed, all of these parameters, the DST, the KP, the flux, and the sunspot number, they all fall in the negligible or quiet regions. And that same goes for all the other time frames that we looked at. 1 month before the earthquake, and then 1 month right after the earthquake.
But you said your model took account of sun activity or something.
Yeah, but it's basically just to make sure that there wasn't any other disturbance that could cause this.
So that data wasn't fed into the model.
Right, the model takes in, it does take into account some of these things, but
it's not from actual data.
Yeah, I think it's from what we expect it to be or something.
It's a climatological model. Just, it's looking at, okay, if I have that kind of flux coming in, that activity in the Earth's magnetic field, what's going on at the surface of the sun, sunspot number, and so what do I project the distribution of the electron?
So you have to input what you think the sunspot activity is to the model,
right,
rather than getting data.
Right.
Right.
So basically, we ruled out these effects for the cause of this disturbance. So basically, all of our evidence suggests that this disturbance is caused by seismic activity. So to kind of conclude all of this, the average ionospheric behavior is known to be well predicted by this PIM model. So I reviewed these predictions for the ionospheric electron density around the fault lines over Haiti before and after the earthquake. And then I compared these predictions with the real data from the Demeter satellite. And then I was able to observe these ionospheric disturbances just before the earthquake, and then they recede right after the earthquake. And then the magnetic field and the solar effects were ruled out as the cause of this disturbance, which leaves us with the seismic activity being the cause. So there's still lots of work to be done on this project. More work is required to definitively rule out all other possible causes of this disturbance. And there are also limitations in the Demeter data. So we got this data from a satellite, so our data was limited to a specific height and a specific latitude and longitude above the Earth. We would like to be able to collect data for all different heights and then all around the globe. So to do this, we would like to investigate the potential for using networks of GPS satellites, such as the Japan GeoNet system, in order to collect this data. We also need to develop more long-term statistical data on the behavior of the ionosphere above fault lines. So one goal for that would be to install sensors along the fault lines in Haiti in order to collect this data to better understand this phenomenon. So with that, I would like to thank Dr. Cornley, as well as Dr. Free, and Dr. Danielle, who helped us with the PIM model estimates, Dr. Perot, who helped us with the Demeter data, and thank you all for your attention.
Any questions?
Is there any suspected cause for how an earthquake could be related to electron concentrations in the ionosphere, or is it just a correlation right now?
Well, there is a theory behind it. So I tried to explain this a little earlier, but before an earthquake, the rock in the Earth's crust gets really stressed, and that causes basically the rocks to create an electric field. And then that effect basically propagates up into the atmosphere. And then because the ionosphere is made up of all these charged particles, you can see the effects of that in the electron density.
There are piezoelectric materials? Yeah, so they're materials that if you compress them, they will develop charge on the surfaces. So like if you go back to the 50s, before your time, the old record players, well, that's exactly the way. The needle was a piezoelectric material, and it ran in a groove that flexed it back and forth. That produced a voltage that they amplified, and that's the way it worked. So,
any other questions?
So go back. I'll ask. Come on, somebody else ask some questions. Go back to your model.
Okay. Where it kind of explains what it was.
Yeah. Yeah, one more or two more.
Yeah, back. Oh, here's the scroll. Right here.
Okay, so the parameters you just put in and see what the effect is. You don't have real-time data or something that you're feeding into this. Or,
Right. So that's why it's an average behavior. On any given day, the model can be off by some value. So there's a delta that's not represented in the model. And that's it. That's the weakness of the model, actually. Because it's not being evolved in time. It gives you an average behavior.
Yeah. If you, like solar activity is delayed by 8 days or something, so you have to, if you were doing that, you have to delay it or something. So go to the next slide then. So this is where you just fed in different parameters to the model?
So basically we would give in the parameters, and then it would give one of these curves. This is actually an ensemble of many different curves for this course of time. So this just gives an average.
Like 5 or something. 1, 2, 3, 4, 5, 6 maybe.
Right. So
5 or 6.
Yeah, I think the point that's missing here is that these curves are being found by looking at the same trajectory that those satellites took, looked at, and then try to have the model predict for the same trajectories what the electron density will be.
So you played with the parameters trying to get it to look like...
Right. We fed the model, a certain altitude and latitude and longitude, and say, okay, at this altitude for this latitude and longitude, give us what this value will be in these points.
With a certain sunspot activity.
Right. The only difference is that we did it every 4 days or every 5 days. We didn't do it for every day.
Sure.
So that's why it's sparser than the other one is fuller than it, because we didn't do it for every day. So.
Yeah, eventually we'd like to get a lot more of this data to solidify it.
Okay, so go forward. Actually, so this was the month before.
About 4 months before. About 4 months before.
4 months.
So basically this is comparing with this.
Yeah. It looks like the majority of the data took a very low-level path here or something. It's hard to tell, but
yeah, a lot of it goes here, and then
some
of it goes up here. Yeah, whereas for the model we only had 5 or 6 data sets. This one we had, I think, 60 or something.
Every day, you have 2 a day or something like that. So because you have the model for all these points, time consuming, but it'll be good to run it for all these points.
Yeah.
So, I guess if the solar flux have people compared this like between January and June or something, and
yeah, so that's why you put a day, because there's a certain climate variation in a day,
right.
Whatever what climate you're in, that is accounted also in the model in terms of what that does to electron density distribution. So you put a day, that day accounts for that time of the year.
We actually looked at the data for in the middle of the summer, like the year before and the year after the earthquake, and it was a completely different shape.
in the middle, all of them in the middle of the summer?
Yeah, so we took the month of June in 2009 and the month of June in 2010, and instead of like this hump, it was kind of increasing up towards here in both cases. So I expect that's from the seasonal change.
Any more questions?
I have one quick question.
Yeah.
So, well, a So that's a simple one.
Yeah.
Another question is, I guess related to that, is who has access to this? And then third is, who else is doing research in this area?
I believe the Demeter data from the satellite, is that open to everybody?
Yeah.
Yeah, it's pretty much open. I think some French group sent up the satellite, and then there's just a website basically you can log into and then retrieve data from any of those
You have to make a request to a group to give you some sort of account, and then you can log in and just grab data.
So, are there any other groups or any other schools that are using it for this particular kind of project?
I'm not sure.
The Boogie University of Toulouse have used this data. They've published some papers on it, and they have some very inconclusive so I think what happens in their publication, they try to look at too much data. So that's a problem too, right? They looked at data around 3 continents, and they're trying to make correlations and trying to develop a prediction, earthquake prediction based on that, and what they came up with is a lot of false positives. So I think my interpretation is that they try to bite too much at one point. They should have concentrated in one area and look at it extensively. So that's really what we're trying to do. And the other thing is, this is kind of a proof of concept, because this data is not sufficient to do what we're doing, but we wanted to see what we could get out of it. So it's kind of, if it can tell us anything, so can we take that and move into a much larger platform, like Mike was saying. Really the way to go is to use GPS data. That's really the way to go.
Yes. So maybe one last question.
Yeah.
So as far as you can tell, how early, or how long before an earthquake actually happens can you actually say, I see enough happening to make a claim?
Yeah, that's a good question. So from the data that I've looked at, so here's 4 months, and you see a little bit of a hump. I mean, I probably wouldn't call that like definitely an earthquake, but it's not on here. But about 2 or 3 months before the earthquake, that hump starts to get bigger. Where 1 month right before the earthquake, it peaks out right here. So I would guess probably 1 or 2 months.
So if this were to actually prove to be accurate, I mean, a month is a good amount of time.
Yeah.
So when I started this a year ago, I was doing just one single plot. So I'll go each month and do one plot, right? And when we try to publish this, the first thing that they told us is, well, how do you know that if you look at what's happened over the entire month that you're going to have the same behavior? Well, here it is. So that's what Michael's contribution was, is to look at an ensemble behavior, rather than just that one day each month you're picking up a value. So I think we have enough data here to publish this work, because we've addressed, and the other thing that they had is, okay, so how do we know this didn't come from anywhere else? Did you look at whether there was disturbance in the magnetic field? Did you look at whether there was a magnetic storm? Or whether the sunspot numbers on the Earth's surface were agitated and all that? And so we looked at all that. So I think we've addressed most of their concern, and we should be able to publish this, I think.
Any other questions?